Now let us state and prove this lemma. We'll call it lemma 2a. Let G be a topological group, and F is a compactly supported continuous function on G. Then for any epsilon greater than 0, there exists a neighborhood V of the adjacent element of G such that the absolute value of f of x minus f of y is less than epsilon whenever y inverse x is in V or xy inverse is in V. And by symmetry, you know, it suffices to prove it just for one of those two cases. So let's prove this. Let us first reformulate this statement. Notice that you can always write x as y times y inverse x. And as a result, you have the following reformulation. Which says this absolute value is less than epsilon whenever y inverse x is V is equivalent to that the absolute value of f of yz minus f of y less than epsilon whenever z is in V. Because here z will correspond to y inverse x in this situation. And as I just told you, it suffices to prove this, because this case, by symmetry, can be proved similarly. So now let's see how to prove this. Let K denote the support of F, which is a compact subset of G. Here we're going to use a common trick in real analysis. Whenever you see a compact set, there's always a step to cover it with finite many open subsets. And to associate this to the continuity of F, we're going to choose those finite many open subsets that correspond to the local continuity of F at each point in K. And that will give us a finite cover. So let me briefly summarize this idea. So we're going to cover K with finite many open subsets corresponding to the continuity of F at each point of K. Specifically, what we are going to do is the following. For each y in K, since F is continuous, there exists an open neighborhood Uy containing E. If you are familiar with the other videos I made, I often use this notation to denote an open neighborhood of some element, with a circle around this common notation of the membership of an element, such that the absolute value of f of yz minus f of y less than epsilon divided by 2, whenever z is in Uy. We can do this because of the continuity of f at y. And another common trick in topological groups is that we can always choose this neighborhood to be symmetric. Now choose a symmetric neighborhood Vy containing E such that Vy times itself is also containing Uy. Hope you are familiar with this trick in topological groups. Normally, to take a symmetric neighborhood, we can, if this Vy is not symmetric by itself, then we will take the intersection of Vy and Vy inverse if necessary. And to make this happen, we're going to use the continuity of the product in topological groups. This product map in topological group is always continuous. This sends xy to x times y. Since each v sub y is still an open neighborhood of E, we can form an open cover of the compact subset K. Then we still have K containing the union y times v sub y, where y ranges in the compact subset K. Now, since K is compact, we can reduce this open cover to a finite subcover. Namely, there exists finite many elements y1 through yn in K, such that K is contained in the union of those finite many subsets. Now let V denote the intersection of those finite many open subsets without this y sub I translation. We're just taking the intersection of those v sub yi's. They are all open neighborhoods of the identity element E. So this is again an open neighborhood of E. And we claim that this V is precisely what we want. We'll show that this V is precisely what we need to make this green part hold, or this part with blue underline. The rest of the proof will consist of the triangular inequality tricks. There will be two cases to consider. First, if y is in K. Remember, K is the union of those guys. If y is in K, it must be in at least one of those members. Say y is in y sub I times v sub yi. Then, for any z in V, we're going to study this absolute value, and we'll break it down by triangular inequality. By triangular inequality, this absolute value f of yz minus f of y is less than or equal to we'll insert f of yi and we claim that both of those two parts are less than half epsilon. The first guy is less than half epsilon because if you look at yi inverse times y times z, this guy lives in y sub I inverse times, remember y is taken from yi times v sub yi. And this z is taken from v. And this y inverse cancels with yi, so you get v sub yi times v. But v is the intersection of all those v sub yi's. So this is again contained in v sub yi times v sub yi, which in turn is contained in u sub yi. Because remember at the beginning we chose v sub y so that its product with itself is contained in u sub y. But for any z in u sub y, we have this inequality hold, which is precisely needed in our situation here. And this verifies this, why this absolute value is less than half epsilon. And now let's look at this part. This guy holds because if you look at y inverse times yi, y inverse is in the inverse of this, which is v sub yi inverse times yi inverse. And we'll add y sub I at the end. They cancel out, and what is left is v sub yi inverse. But at the beginning, we took v sub yi to be a symmetric set. So this inverse is same as just v sub yi. And again, this is contained in u sub yi. There are assumptions in here. And this justifies this where this guy is also less than half epsilon. In the end, you get this absolute value is less than epsilon. This finishes our first case when y is in K. For the second case, namely if y is not in K, then for any z in V, we look at f of yz minus f of y. In this case, remember, this K is a support of f. So if y is not in K, this guy is 0. So this will be equal to just f of yz. And now there are two subcases to consider. First, subcase 2.1. If yz is also not in K, then f of yz is also equal to 0. So there's nothing to prove. They are both 0. So this epsilon value is 0. And of course, this is less than epsilon, which is a trivial case. Second, if yz is in K, then because K is a union of y sub i's times v sub yi's, where i's from 1 to n, we have this yz must be in y sub I times v sub yi for some I. And if you move y sub I to the left hand side, you get y sub I inverse times yz is in v sub yi. So if you look at f of yz, absolute value, applying the triangle inequality, you get this is less than or equal to f of yz minus f of yi absolute value plus f of yi absolute value. The first part is less than half epsilon by the same reason as above. But the same argument as here, you can see that this absolute value here is exactly the same as the situation here. So we get this guy is less than half epsilon by the same argument as above. The slightly tricky part might be this part. Why must this part be also less than half epsilon? This guy is less than half epsilon because the absolute value of f of y sub I is equal to f of y sub I minus f of y. And this guy is less than half epsilon. Here we can insert this minus fy because f of y, remember, is 0. f of y is 0 because y is not in K. The K is a support of f. So if y is not in K, then f of y must be 0. And this part will follow from the continuity as well as the manipulation of sets. But let me carefully write this down. We have this inequality because y inverse times y sub I, which is equal to y inverse times y sub I times z times z inverse. So we add and subtract z and z inverse. So we essentially add something that is identity. But this product of four things is actually equal to v sub yi times v inverse. This part is okay. The inverse must be in v inverse because we took z to be in v. And this part is in v sub yi because of our argument here. We showed before that the product of those three things is in v sub yi. And now, what is this guy? This guy, first, by the symmetry, is equal to v sub yi times v. Notice that here v is also a symmetric set because v is the intersection of n minus symmetric sets. So itself must be symmetric. This is obvious. And because v is the intersection of those v sub yi's, in particular it is contained in v sub yi. And v sub yi times v sub yi is contained in u sub yi. Now we have shown that y inverse times yi is in u sub yi. Now by the continuity we start with, we have this epsilon value is bounded by epsilon divided by 2. So this guy is less than half epsilon, and so is this guy. In the end, we get the absolute value of f of yz is less than epsilon, which is same as saying that f of yz minus fy has an absolute value less than epsilon, because f of y here is 0. So we are done with this second case in this lemma, which combined with our first case finishes the proof of this green part, which is equivalent to this underlined blue part. And as I remarked at the beginning, for this case, the proof is very similar, so we omit that. Anyway, we proved this whole lemma.